All right. It is July 4th, and we're not meeting as a class today, but I am sending out this video to help you get started on the next homework, which is actually due on Tuesday. We may extend it a little bit till Wednesday just to give you some extra time to finish. But we are going to be working on momentum, I believe. We just finished work and energy, and we have linear momentum coming up here next, so that's what we got going here. So if I take us back one here and go to the book, let's take a look at what momentum is for a few minutes, and then we'll go ahead and take a look at some of the homework in the assignment so you can get started on it. So, Chapter 8, Linear Momentum. So we just finished with energy, and energy and momentum are actually kind of similar, and they were often confused for one another. But one thing that is very different about momentum from energy is that momentum is actually a vector quantity. The energy quantities that we talked about, work and potential energy and kinetic energy and everything else, they didn't matter which way you were going. We did have negative and positive, which meant that the energy was either entering or leaving the system, but it didn't matter which direction you were going in space. Whereas momentum definitely cares about that. And momentum is calculated, just the magnitude of the momentum is calculated by taking the mass of an object times the speed of that object, and that'll give you the momentum as long as they're going in a straight line. And so we can calculate that in this problem here, where you have a football player running at 8 meters per second at 110 kilogram mass. So you can calculate that momentum quite easily. And you can also calculate a ratio between the momentum of the player and the momentum of the ball that they're catching, where the player is 880 kilogram meters per second, and the ball, which is moving faster but it's much, much smaller, has a momentum of 10.3. And so the player is 85.9 times more momentum than the ball. And you can do this also with a bullet in a person, for example. A bullet that's moving at faster than the speed of sound has very little momentum compared to a player. And so while the bullet can do a lot of damage because it has a lot of energy, it's not necessarily not very likely to push the player very much, because momentum is the ability for something to push. It's the ability for something to cause a force to occur. And that's where this comes in right here. Newton's second law and momentum are related, where the force is equal to the change in momentum over change in time. So force causes a change in momentum. If you have a net force, it's of course, if all your forces add to zero, then you don't have a change in momentum. If you let that change in momentum equal the mass times change in velocity, or change in mass times velocity, that's mass times acceleration. Then you get, for the net force, you get mass times change of velocity over change in time, which is the mass times acceleration of an object, and that is, of course, Newton's second law. So it's kind of a derivation of Newton's second law. And as we go back here to this definition of momentum, force equals change in momentum over change in time. A change in momentum over a certain amount of time is what we call an impulse, which is, of course, a force. Is related to a force. So let's take a look here at Venus-Williams racket problem. Venus-Williams hit the fastest recorded serve in a Premier Women's match, 58 meters per second, and we want to know the average force exerted by the tennis ball if the racket hit the ball for 5 milliseconds, and the ball's speed right after that is 58 meters per second. So The change in momentum, of course, it goes from 0 meters per second to 58 meters per second. And multiply that change in velocity times its mass right here, and you'll get the change in momentum. Put it over the change in time, and you put that over 5 milliseconds, 5 times 10 to the minus 3 seconds, and you get an impulse of, you get this impulse going on, and it's a 661 Newton force, or about 660 newtons. And that's quite a bit of force. That's, a force that's equivalent to kind of a mass of an average smaller person. And here they actually define the impulse. That change in momentum that's in the equation is the impulse. And you can actually calculate by taking the net force on an object over the time that it's acting. So that if you know the force and the time that the force acts, force times time becomes impulse, which is the change in momentum. So here we're going to calculate the impulse of a billiard bar striking a rigid wall. We have a ball that strikes the wall perpendicular to the wall at 90 degrees, and another one strikes the wall at an angle of 30 degrees. And we want to calculate the impulse, and of course, each one of these is going to have a different. Excuse me. Each one of these is going to strike the wall with the same speed, but with different speeds perpendicular to the wall, because the speed is just the speed of the ball, whatever direction it's going. One of them is going directly towards the wall, the other one is going 30 degrees to the wall. So for the first one, so for the first one, you have a ball that's coming in with a particular momentum and leaving with the same momentum, but its change in momentum is actually double its original momentum, because it goes in a positive direction, comes out in a negative direction, and the difference between a positive direction momentum and a negative direction momentum is actually twice that momentum. And you can kind of see that, let's see, where do they don't really calculate it here. They kind of do here, I suppose. So anyway, you have mu and negative mu, and then when you take the difference between those, it's negative 2 mu, because you take the final minus the initial. So it's negative mu minus an mu, which is minus 2 mu, or where u is they're using u for the velocity at this point, or the I don't know why they do that, but they do. And then the second ball, when it comes into the wall, it's mu times cosine 30, because we're only taking the momentum that is perpendicular to the wall. And so it comes out with a much smaller momentum. It has a change in momentum that's much smaller. If you do a force versus time graph, then the area underneath the curve of the actual force is going to actually be the momentum. And why do we talk about momentum? We talk about it because it is one of these quantities that is conserved. And it turns out that momentum is one of the quantities that is absolutely conserved in the universe. It is always conserved. It's not like energy, where energy can sometimes be converted into mass. Momentum is always conserved throughout the universe. We've never been able to observe a situation where it is not. It's not always obvious, but it is always conserved. And so it's very important. Anything that is conserved, where the beginning amount of stuff that you have is equal to the end amount of stuff that you have, always, 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 then you can use that to solve things and to figure things out. So that's very important. So we have these two cars, mass 1, mass 2, and they're moving towards each other, and they hit each other. And before they hit, they have a momentum 1 plus momentum 2 equals the total momentum. And then afterwards, they have momentum prime 1, which is the final momentum, plus momentum prime 2 equals momentum total. So they have to equal each other. So you can just set the sum of the first momentums equal to the sum of the second momentums. And when you're talking about a single dimension like this, just cars going back and forth, it's pretty easy, because you just have to consider things going to the right to be positive, things going to the left to be negative momentums, and you're good to go. However, this is not only true in one dimension, it's actually true in all dimensions. It's true in 2 dimensions, 3 dimensions. So momentum can be conserved in multiple dimensions at once. Here they talk about isolated systems versus momentum in conservation in general. And what they really mean here is that if you account for everything, if you account for all of the momentums, then momentum is always conserved. But it's kind of hard to do that. So what we do is we try to look for isolated systems where there are no forces acting on that system externally, so that we don't have to consider any momentums that are being transferred into or out of that system. And then you can say that the momentum is conserved. Excuse me. Here's an example of a system where the momentum is being conserved. You have this rocket that is following a path up through space, and it's being acted on by gravity. So the next net force in the y direction is gravity, but there's no other force acting on it. But then all of a sudden the two parts of the rocket actually split apart. And you'll find that as they split apart, the center of mass actually is between the two parts of the rocket. And that center of mass will follow the same parabolic path that the center of mass of the rocket would have followed. And that is because of the conservation of momentum. Momentum says that this thing and this thing are going to have separately momentums that will add together to be equal to the momentum of this thing. And one of the results of that is that the center of mass will follow this same path that it was following before. Very small particles, with very small particles, atoms and smaller, it's actually very simple, very easy to prove that they have conserved momentum. And there are many, many examples of that. They're showing some of them here, but they're very. It's a very simple thing to demonstrate that. In this next part, 8.4, we're going to talk about collisions and the conservation of momentum in collisions. We're also going to talk about conservation of energy in collisions. So we're going to start with a very simple type of collision, which happens in very specific circumstances, called the elastic collision. A perfectly elastic collision is one where kinetic energy is conserved, internal kinetic energy is conserved, and also momentum is conserved. So here's an example. You have a frictionless surface, and you have these two blocks, and they bounce off of each other in a perfect situation, like they bounce without losing any kinetic energy. And usually that happens in situations where the objects are extremely elastic. Hard rubber balls, billiard balls off of the walls, and things like this, things that bounce really well, super balls and springs and things like this. But it's in the macrocosmic world, even those things are not perfect. Usually you have to go down to the atomic or subatomic level to see perfectly elastic collisions. But magnets do pretty good elastic collisions when their north poles are facing each other and everything else. But anyway, what you'll see in a perfect elastic collision is that the momentums before the collision and the momentums after the collision will be added together to equal the same amount no matter what. And same with the kinetic energies. You can see here they've done that. So if you want to know the speed of two things after a collision, and you know something about the speeds before the collision and maybe the speed of one after the collision, it's pretty easy to do using the momentum equation. A little bit more work to do using the kinetic energy equation, but if you have an elastic collision, you get two equations. So you actually have the momentums have to add to be constant, the kinetic energies have to add to be constant, so all of a sudden you have two equations. Even if you don't know the final two energies, you can calculate them because you have the two equations and you can solve for two unknowns. And that's exactly what they're going to do here. We have two objects that are mass 1 and mass 2 here, and they give us velocity 1 and velocity 2 at the beginning. And we want to solve for the velocities at the end, so we use the two equations. The momentum initially plus momentum equals momentum final. In this case, one of the initial momentums is 0. And then the kinetic energy initially equals the kinetic energy final. We have two equations that have two unknowns. Take the momentum equation, solve it for one of the velocities, the final velocities, plug it into the other equation, and into the kinetic energy equation, and solve for the other velocity. And then once you get one of the final velocities, plug it back into one of the original equations, and solve the whole thing. It's not really all that hard. When this starts to get hard is when we enter into multiple dimensions. All right, next thing to learn is about an inelastic collision. Now, a perfectly inelastic collision is where two objects will collide with each other, and then they will stick together to become one object. And in that case, kinetic energy is not conserved, but momentum is still conserved. And so, a perfectly inelastic collision, the two objects have to be connected to each other and stuck together when it's all done. And here we have an example of that, of a hockey player catching a hockey puck. And they give you the mass of the player and the hockey puck. And what you're going to do is you're going to solve the conservation of momentum equation as if the two masses at the end are combined. So you take m1 plus m2 times just one single velocity, because they're one thing now. And once you've done that, you get this new equation to solve for initial velocity or final velocity, whatever you want to solve for. You can just use this equation. Which is what they do. They use it to solve for the final velocity. Then they can solve the final kinetic energy. Okay, so what happens if we end up with a two-dimensional situation? This is where it gets really crazy. So here we have a billiard ball coming in and hitting another billiard ball. The initial momentum of the first one is this velocity times the mass of this ball, and it's in this direction, to the right, so it's in the x direction. But then the final momentums have both an x component and a y component for the purple ball and for the red ball. And what we discover is that the x components have to add together to equal the original x component momentum, and the y components have to add together to be equal to the original y component momentum. In this case, the original y component momentum is 0, so these two y components over here will have to add up to be 0. But you end up getting two equations again, at least, with two unknowns that you can solve for. And you can see they're solving for these, and we're going to have sines and cosines and angles and everything else. But you do have to conserve momentums in both dimensions. So here we have an object that's sliding on a surface, strikes another object, they go off at angles, and we want to know the magnitude and direction of the second object. They tell us the magnitude and direction of the first object, and after it hits, they want to know everything else. So what they're doing is they're doing this in a dark room, so you can't really see what's going on. You're measuring things outside the room, but you can get angle and you can get velocity and everything else. And they're just doing exactly what was done in the previous example, where you have the momentums in the x direction initially, which there's only one momentum in the x direction initially, have to equal the momentums in the x directions finally. So you have two things that are moving, and they both have an x direction momentum, but you get those by multiplying by cosines of angles, right? And then you do the same thing in the y direction, where initially in the y direction there is no momentum. And so it's 0. And then there's momentum in the y direction for each of these two objects that have to add together to be equal to 0. Now you have two equations, and again two unknowns. And so you can solve for the unknowns. And in this case, when you're solving for one of the unknowns as an angle, it's often a good idea to take a ratio of the two equations so that you end up with some tangents. And that way you can get tangent of theta and solve for the theta in one instead of trying to solve for it in several. It'll help you to figure it out. So whenever you're solving for a theta and you've got sines and cosines and equations, create a ratio equation. Divide one of the equations by the other equation so that you get a sine over a cosine and you can solve for that tangent. Very helpful. Okay, they do one with two objects of equal mass, two equal mass balls, and you find that the angle between them is always 90 degrees, which is kind of interesting. Then they do a rocket propulsion problem, because in rocket propulsion, when you're accelerating a rocket using a gas or a fuel of some kind, what happens during the fuel burning stage is that it actually loses mass. So the mass of the rocket is changing. And that means that the momentum equation has this mass that's changing, delta m over delta t. And so you get an acceleration that has a changing momentum, which is really quite interesting. delta n over delta t there. So that's an equation you need to use for doing rockets. And I think that just about covers us for this chapter. So I will actually go ahead and post this video, and then I will post another video discussing some of the homework problems. Assuming we don't have any more, I don't think we have any more. There's another equation at in this rocket propulsion one. Nope, there isn't. So we're good. But I will go ahead and post this video, and then I will make another video and go over some of the homework problems and get you guys started on those.